Hello guys, first of all, it was a really bad movie, the one which I watched today. Anyhow, second of all, after there is something called environment fair. Now there is something going on, that is Netaji Subhash Chandra Bose fair. Okay, so people are making money out of the Biplobis and all. So still the sounds are very much over here. Still then we have to complete biomolecules and we will do the same. We have already completed the number of tests that are for glucose, and again we will come to the structure of glucose. Okay, so see, we have already studied that glucose has a open chain structure and we have established that, right? But does glucose really have an open chain structure? We have proved it, right? We have already proved it. Then what happened? The thing is that we have already proved it has a free OH group, it has a free CHO group, but there are certain reactions which also says that maybe glucose may not have free OH or free CHO group. The structure may not be open chain type. Let's see. It doesn't form any addition compound with NH3. It doesn't respond to NaHSO3 test. These are all tests of ketonic group. Aldehyde shall give this, right? It doesn't happen, man. No response to 2,4-DNP test. No response to Schiff's test. All this is characteristic reaction of aldehyde group. Doesn't react, man. Next, Pent Acetate of glucose. It doesn't react with NH2OH. It should, right? There is a carbonyl group, it should have reacted with NH2OH, hydroxylamine, but it doesn't react again. So it's like गजब बात है यार. अभी हमने प्रूफ किया कि इसमें फ्री OH है, फ्री CHO है, ओपन चेन स्ट्रक्चर है, लेकिन ये सब रिएक्शन मिला के हो गया, नहीं भी हो सकता है यार. So there come another study right now, then what exactly it is and how does this work. So first of all you will copy all these things, okay, and then we will come to the next part. So you have already gone through, you have written down those things. Now there is another part, that is open chain structure also doesn't explain other things. So we have to go through those also. Number one, it doesn't explain the glucose in two forms. There are two forms of glucose. One we know, D and L form, that we already know. But other than that, even within the D form, we have alpha and beta. Abhi kya hai alpha and beta we don't know. We are going to study it. So don't worry about it. At this moment, you just know there is alpha and beta type of glucose. These are having certain difference in properties, and there is existence of these two types of glucose. But our open chain structure doesn't explain that, so we have to go through that. Now how do we prepare alpha D glucose? If we have a concentrated solution of glucose at 303 Kelvin, we will get alpha D glucose. If you take that and heat it up, so hot and concentrated solution of glucose at 371 Kelvin, almost 100 degrees Celsius, you will get beta D glucose. Okay, so you have seen that there is formation of two kinds of D glucose only, but which are having different properties, and it really doesn't help understanding this two by the open chain structure. So there must be some other structures which I need to go through. Second thing, it doesn't explain something that is called mutual rotation. What is mutual rotation? Mutual rotation is change in specific rotation of optically active compound with time to an equilibrium structure. Now the thing is that you really have forgotten what you have studied in class 11. In class 11 you have studied in optical isomerism, there is something called specific rotation which used to be denoted by alpha D. थोड़ा 11 के बुक में जाओ, जनरल प्रिंसिपल्स ऑफ ऑर्गेनिक केमिस्ट्री में ऑप्टिकल कंपाउंड्स में ये वाला मिल जाएगा कैसे कैलकुलेट होता है. So you have also done some problems on it, at least one or two problems I have done in my class only, so you can refer that also. How to calculate the specific rotation and stuff. So what happens is there is a structure called alpha D glucose, there is a structure called beta D glucose, two different compounds. Now this alpha D glucose have certain specific rotation. Specific rotation means the amount of angle the light is going to get rotated, the plane polarized light is going to get rotated while you pass through this alpha D glucose. Okay, so there is some amount of angle, and that amount of angle for alpha D glucose is 112 degree. For beta D glucose, that amount is 19 degree. Now when you put all this thing together, there will be some change in specific rotation of this optically to these two optically active compounds, and at the end of the day, due to this change in specific rotation from one form to another, you will form an equilibrium mixture which will be having one kind of average specific rotation 52.7 degree. So when you put alpha D glucose and beta D glucose together, it is going to form an equilibrium mixture which will be having a specific rotation of 52.7. If you take that separate, it will be 112, 19, but when you mix that two, it is 52.7. So what happens is, even if you put only alpha D glucose, after certain amount of time, it is going to change its direction and it is going to form an equilibrium mixture with beta D glucose, and at the end of the day the angle will be same. So that is why it is said change in specific rotation of an optically active compound. इसको डाल दो, ये optically active है, इसका specific rotation धीरे धीरे change होगा, ये थोड़ा beta D glucose form करेगा, beta D glucose थोड़ा alpha D glucose form करेगा. At the end of the day, there will be equilibrium mixture of having certain percentage of alpha D glucose and certain percentage of beta D glucose, 64 and 36% approximately, and they will form equilibrium mixture of the both, right? And believe me, in this equilibrium mixture, the open chain structure will be less than 0.5%. Okay, so obviously we are going to come to the closed chain structure after this. So this mutual rotation part is not explained by open chain structure. This is not explained by open chain structure. Now last one, glucose with CH3OH, it forms alpha D glucoside and beta D glucoside. Now these glucosides, if you want to know the structures of glucoside, the structures of glucosides are also important over here. Just a second. Okay, so glucosides means you can, if I'll just show it over here, CHOH whole 4, and here suppose it is CH2OH, and if you put ROH and dry HCl gas, then what happens is this CH will remain unchanged in a CHOH whole 4, and this will become CH2OCH3. Okay, so this is glucoside, but see, if you see this glucoside, it still have the aldehyde group, right? So it should give the Tollens and Fellings reagent test, but unfortunately it doesn't give, right? It doesn't give, it doesn't react with HCN. So there must be something different, has to be, right? There has to be something different. So what we suggested over here is, chemists suggested that if it doesn't occur, that means there must be a structure which is one kind of hemiacetals. Now what is hemiacetal? If you take this ketonic structure and react with ROH, it will form this. So this part will change to OR and this part will be OH, and again you put another molecule of ROH, then both will be OR. So this is hemiacetal and this is acetal. This is hemiacetal and this is acetal. This hemiacetal formation is important, because if this hemiacetal get formed, then we will see at the next part we are going to discuss. If this hemiacetal get formed, then this Tollens reagent, Fellings reagent reaction won't occur. You will not have any free aldehyde group. Okay, neither HCN will react, that we will see. Okay, so now you copy all these things, and after that we will be dealing with the formation of the cyclic structure of glucose, something that is called pyranose structure or Haworth projection. We have already done the Fischer projection, but that is for the open one. We will do it for the closed one also, the Fischer projection, pyranose structure or Haworth projection. इसको copy कर लो. Hello guys, so now that we have already known that how hemiacetals get formed, now it is time for us to change the open chain structure of glucose to closed chain type, and it is very easy. Don't get confused, look at my steps, follow that. it will be crystal clear. Believe me, give me 5 minutes and give yourself 5 minutes, it will be crystal clear. Easily you can draw this. Okay, so see, first of all you look at this structure. This is glucose structure, open chain, right? At only C3 position from the top there is change in OH will be the left side. Okay, so you look at this structure very well. This is glucose open chain structure. Okay, in this structure you have a CHO group, you have a OH group. Okay, you have a CHO group, you have a OH group. So can we form an intermolecular hemiacetal reaction? Is it possible? Let us check. Step 1 is this one. This is step 1. So in step 1 I am going to break this bond. Okay, I am going to break this bond, and what I am going to do, I am going to write this H. Okay, now it's just H. This will be different, third carbon, then OH, H, 4 ho gaya. Now here is a bond of H. Let's take on this side H. This bond is broken at this moment. This bond is broken. This OH I have to connect somewhere, right? Okay, you will see CH2OH. Now what I have done over here in step 1, I have disconnected this bond and I am asking this bond, this OH to go over here. So let's connect this OH over here. Here there is already an H. Now it at this moment how many bonds are there? 5 bonds. So this oxygen does not need another bond, right? This oxygen does not need another bond. As soon as OH comes, it can only share 1 electron with that oxygen carbon. So this is the condition. This is also requiring 1 bond, this is also requiring 1 bond, and hence we can definitely connect this like this. Okay, we can definitely connect this like this, and this is number 1 carbon. Okay, so this is cyclic structure alpha D plus glucose. Done. This can have another isomer of it, optical isomer, that is this one, C, 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 3, 2, 5, CH2OH. This will be connected like this. At number 3 carbon there is separate. Okay, number 3 पहले ड्रॉ कर लो, उसके बाद OH, H, OH, H. Now on this one, in this number 1 carbon there will be change. Change means here it will be OH and here it will be H, and this is beta D plus glucose. हो गया? Just at number 1 carbon the configuration changes. The difference between these two is C1 carbon, and this carbon is called anomeric carbon. This carbon is called anomeric carbon, and these two, alpha glucose and beta D glucose, are called anomers. So this alpha and beta, these things, these two are called anomers. Okay, so this is anomeric carbon, number 1 carbon is anomeric carbon, and these two isomers are called anomers. हो गया? These two isomers are called anomers. Can you now follow this step 1 and step 2? This was step 2, right? This was step 2, connecting this carbon with this oxygen, which I have done. Okay, this was step 2. So you can easily do it. Practice it once. It is very easy, not hard. Okay, And this kind of projection of glucose is called Fischer projection. Please copy it, copy कर लो, ठीक है? Copy it by yourself, try to do it by yourself. It is very easy. It is important for you to transfer from Fischer to Haworth also, which I will teach right now. But at this moment, how to convert open chain to closed chain. Okay, alpha D glucose, beta D glucose. Problem is solved. Mutual rotation explained. Mutual rotation is explained. Formation of alpha D glucose and beta D glucose is very well explained by this kind of structures. Okay, copy it. Hopefully you have copied everything. Now I am going to rub only the upper portion because I don't have space, and you will do all these things in the lower portion of this Fischer projection. Now we are going to do the other projection, that is called Haworth projection. Okay, we are going to do Haworth projection from these structures. So this is alpha D glucose. We are going to form cyclic structure. See what I will do. First of all, write O, and at each point of hexagon give carbon. ठीक है? This is carbon number 1, 2, 3, 4, 5. ठीक है? Fifth carbon, that is, if you number it from 1, 2, 3, 4, 5, 6. Okay, now in the second carbon, one by one you will see. First carbon we are going to do first. Hydrogen is in the left hand side. Whichever is in the left hand side, put it on the top and the other on the bottom. Next, same. So put it on H on the top, other on the bottom. Next, third carbon, there is some difference always in the third carbon. So OH, H. Next, fourth carbon, H, OH. Fifth carbon, CH2OH always on the top. Remember, this one you have to remember. CH2OH always on the top. And niche H. This is alpha D plus glucose. Okay? Next, we are going to draw this. Again, we are following the same methodology. Now it is very easy, I guess, for you guys. Okay? Only in the carbon number 1, anomeric carbon, there will be a change, OH, H. Others you can just copy the D structure. Okay. Now if you see, the difference is only at C1, nowhere else. Only at C1 there is difference. This is beta D plus glucose. Okay? Understood? How did I do it? You have to copy it after this, and this structure looks as pyran. Pyran has this kind of structure. Okay, pyran. This is pyran, and hence these structures are called pyrano structure. Pyrano structure. This is also called Haworth projection. This is Haworth projection formula. It is also called pyrano structures. Okay, so done. You have now known what is Fischer projection, how we will draw Fischer structures, and of glucose you know how to draw pyranos or the Haworth projection of glucose. So basically at this moment we are through with the cyclic structure of glucose, and we are going to now study that how does cyclic structure explain all the properties of glucose that was not getting explained by the open chain structure. That is our next part. So copy it, and we are going to start next. Okay guys, now what are the basic advantages we get out of the Haworth projections? Number 1 is the formation of alpha and beta glucose, the existence of it is explained. Number 2, mutual rotation is explained. All reducing carbohydrates means all monosaccharides, maltose, lactose, that is disaccharides, except sucrose, all exhibit mutual rotation. So remember, sucrose is the carbohydrate that is in your syllabus that doesn't exhibit mutual rotation. Okay, done. Next, reaction with HCN, toluene and phelings. We have seen glucose does react with HCN, toluenes and phelings. Now how does it explain? Because if you see the pyranose structure or even the Fischer structures, the new cyclic structure, then you won't find any free CHO group. Then how does it happen? The thing is that we have already said the hemiacetals form 99.5% and the open chain forms 0.5%. So there is 0.5% open chain form of glucose present in any solution. So this HCN or this toluenes, phelings, this reaction, these are basically strong reagents. Okay, these are strong reagents, and reaction with this and this is irreversible reaction, because they are very strong. Now how it becomes irreversible, I'll show you. If you put this kind of strong reagent over here, this open chain form will react with it and open chain form will finish off. Open chain form diminishes diminish quickly. As soon as in an equilibrium you take out the product, basically what happens, there is an equilibrium between these two, right, and this is getting reacted. So what will happen when this get reacted? This falls to 0%, but 0% is not an equilibrium mixture with hemiacetals. Hemiacetals again undergo equilibrium. The equilibrium is getting disturbed as soon as the open chain is taken away by these strong reagents, and as soon as this becomes 0%, some of the hemiacetals again change to open chain to form 0.5% open chain, and that again reacts. Okay, now while you talk about this, what happens? These are very weak reagents and the reactions are reversible. But how the reactions are reversible? The thing is that when you put the weak reagent over here, diminishes very slowly. Which diminishes very slowly? The open chain. So the equilibrium is not disturbed much, and hence if the equilibrium is not disturbed much, most of the hemiacetals will not change into open chain structure because of this weak reagent, and hence this reagents won't react with glucose, but this will do. Toluenes, phelings and HCN, we have already discussed, this reacts. The reason behind it is this. Okay, so this difference is also explained by the cyclic structure, Haworth projection or the Fischer projection. Okay, so this was important. Next is, if you go for the glucoside one, we have already discussed what is glucoside, right? So what is glucoside? Glucoside is this one. While you have this structure of glucose, so I am not writing everything over here, CHOH whole 3, right? Yes, whole 3, just connecting like this. So here if you put ROH, so it will form OCH3 H CHOH whole thrice C and CH2OH, correct? This is going to get here, there is one H. This is going to get formed, and this is the glucoside we are talking about. This glucoside doesn't have any sort of open chain structure. Why this glucoside will not have open chain structure? Because the thing is that this glycosidic bond is very strong. Okay, this glycosidic bond is very strong, and due to this bond it doesn't have any sort of formation of your toluenes reagent reaction. That is basically it will not give the silver mirror taste. Due to this is one of the reason, and this bond is also taken care out by this R. I have written CH3, this will be OR. Okay, so as soon as this is getting formed, it doesn't react with the toluenes reagent. Okay, because toluenes reagent will react when you have some open chain structure of 0.5%, that is for glucose. But while you form glucoside, this is not the case, and hence it doesn't give you the tolerance test because it doesn't have any free aldehyde group at all, no open chain structure for it. And also this glucosidic bond doesn't break, this is very strong towards the alkalis, it doesn't get hydrolyzed. If it gets hydrolyzed, then it is okay, it's possible, but it doesn't get hydrolyzed, it is very strong. Okay, this linkage is very strong. Okay. Okay, next is another thing that we have studied, that is Pent Acetates. Now in case of Pent Acetates, if you see, this is the, okay, I have already drawn it, I don't need. So if you put CH3COOH over here, what will happen? Here it will be OOCCH3 HCHOOCH3. Okay? Now this is 3, this is C H, and this is again CH2OOCCH3. This will be another C. Okay? So this is the condition. Okay, this is the condition. Now let me see, there will be 2C. Okay. Okay, so is there any free OH group present? There is no free OH group present. So, or there is no free aldehyde group present. So there is no reaction. Pent acetate doesn't react again. Okay, Pent acetate will not react again. Okay, it can react. Now you can say, sir, why doesn't it react with an H2OH? It will not react, man. It doesn't have any CHO group. It doesn't have any CHO group. This compound is different from glucose. This will not have any open chain structure. That may have. The glucose itself will have 0.5% open chain structure, but when it reacts with something else, it forms a compound, it will not have any open chain structure in its equilibrium mixture, and hence it will not react. So hereby we have finished everything of glucose required for ISC, CBSE examination. This is absolutely for board purpose. We have not discussed any MCQs over here. So go through this very well, and obviously we will be coming up videos on fructose and disaccharides, and we are left with a lot of things, man, like protein, amino acids, then your nucleotides, and we will do everything. We will finish it within your board examination. So don't worry, give some time, we will finish it. Thank you.